as a reminder, what's the Laplacian matrix? Well, you take the diagonal matrix of degrees, you subtract the adjacency matrix. All right, good. Now, we want to say a few things. And one of the things we actually said last time was if you take x, I'll say star, you can just use transpose, x star Lx, and I'm thinking of x as an assignment to the vertices. So, label the vertices 1 through n, you have the vector x, x1 through xn. This is the sum over all edges, I adjacent to j, of xi minus xj squared. Okay. Well, one result from this that we can draw right away is that this is positive semi-definite, which is just a nice way of saying, since we're dealing with symmetric matrices, all eigenvalues are greater than or equal to 0. And we can come up with actually many proofs of this, that all the eigenvalues are greater than or equal to 0. We'll do at least one or maybe two more. Of course, they're probably proofs are related one to another, but that's okay. We also saw that if you take L times the all ones, you always get 0 times the all 1, which means that 0 is always an eigenvalue. So now I want to talk about the multiplicity of 0. And can we say something about that? So the multiplicity of 0 as an eigenvalue. And for the Laplacian matrix L. Okay. Well, one of the things that we can do is say, well, look, if we do have 0 as an eigenvalue, it's really saying we need to have x star Lx equals 0. And so we want to go into that. What is that force? Well, we have some I adjacent to j, xi minus xj squared. And I know you're like, oh, what if we do complex numbers? No. We can assume everything's real. That's one of the nice things. We can always assume our eigenvectors are real. So, we have a sum of squares is equal to 0. What does that force on us? Yeah, it forces everything has to be 0. And so, in particular, it says if I is adjacent to j, then xi minus xj has to equal 0. Well, of course, saying xi minus xj equals 0 is the same as saying xi equals xj. Okay. Now we start to think, what does that say about the graph? So we think of the x's, the xi's, we're assigning values to the vertices. And now we've just been told if two things are adjacent, they have to have the same value. What does that tell us about the kind of structure that these x vectors can have?
Constant unconnected components.
Yes, good. Okay, so our conclusion that we are drawing here is that the xi is constant on connected components. And as a reminder, what do we mean by a connected component? It means that we are in the same connected component if between any pair of vertices inside that component, it's a subgraph. We can get from one to the other by staying inside that and taking a walk. Well, of course, if you can take a walk, then you just sort of say, okay, at the start is the same as the next vertex. The next vertex is the same as the vertex after that, and everything just follows along. Okay, so we now know that as long as we're constant on connected components, well, this says we have to be constant on connected components, but the opposite's also true. If we are constant on connected components, then we satisfy this relationship. Okay, so what does that tell us about the dimension of our eigenspace? Now, because we're real, we always know that there's the algebraic multiplicity and the geometric multiplicity. So as a reminder, for those who haven't gone too far down the linear algebra road, algebraic multiplicity is how many times your eigenvalue shows up in your characteristic polynomial. Geometric multiplicity is how many eigenvectors you have for a given eigenvalue. But they're the same. Okay, so back to my question. We know we have to be constant connecting components. What does that tell us about the dimension of our eigenspace for 0?
Should be the number of connected components.
Why do you say that? So why are you saying it should be the number of connecting components?
Because you said that last time.
That's a good reason. Yes. So the dimension of eigenspace for 0 is the number of connected components. Essentially, when we're thinking about dimension, we can think of like how many choices do we get to make? And so what you have is you say, well, for every component, I get a choice. I get a choice of what value am I going to pick for this component? And so we have number of connected components choices. And that gives us our dimension. So there we go. So we now have the nice conclusion that says, okay, cool. So the spectrum of our Laplacian matrix L can tell us the number of connected components. Now, as a refresher, could we do that for the adjacency matrix? I see somebody shaking their head no. Do you know why we can't do that for the adjacency matrix?
I remember you drawing a counterexample, I believe.
Good. Because there's counterexamples. Usually when you go with your smallest counterexample, you get a lot. So that's an example. And if you work through what the eigenvalues are, in fact, we know how to find the eigenvalues of this, because cycle, isolated vertex, star, that's great. So these are co-spectral for A, but they have different numbers of connected components. So something like this can't happen. They might say, that's cool. So does that mean it's a superior spectrum? Well, it depends. If you want to talk about number of connected components, yeah, it is. But maybe that's not what you care about. So there are other things you might care about. Let's see, I believe I have a 50-50 chance of getting this picture right. Okay, yes. So here are two graphs on 6 vertices, and these are co-spectral for the Laplacian. Now, I don't have a quick derivation, but you can plug it into your computer and just check the characteristic polynomial. Usually the characteristic polynomial is the easiest way because it'll have nice numbers involved. Oftentimes the actual eigenvalues themselves are messy because roots of polynomials are messy. Looking at these two, is there anything that distinguishes one from the other?
One of them has a leaf.
One of them has a leaf. Yes, that's true. I saw a hand back there. Yes?
One of them has 2 cycle 4s on it.
Well, this one has 3 4 cycles.
4 on it.
So left, right, all the way around.
Max
Yep.
degree is control.
Max degree. Yeah, one's bipartite. And that's actually a big one. And the reason I want to say bipartite and also triangles, with the adjacency matrix, we can count the number of triangles. And we can tell if something's bipartite. Well, here, we can't count the number of triangles. We can't tell if something is bipartite. So we lose things. So you should never say, there is the best matrix. it's more accurate to say there are good matrices and there are not so good matrices depending upon what application you're using. So every matrix has strengths and weaknesses. And you might say, but maybe we just haven't looked hard enough, Steve. Maybe someday someone will discover the ultimate matrix. And the answer is no. That's a fool's errand. It will never happen. So don't look for it. And, well, I mean, you can look for it, but wait till after you have tenure. Because, it's one of those things. You don't try to prove the Riemann hypothesis until you have tenure. And then go ahead and try to prove it as much as you like. All right, we should, we'll add some comments here. So L cannot count number of triangles. L cannot test bipartite. How about number of edges? Can we tell how many edges we have from the eigenvalues? And if the answer is yes, how do we do it?
It's just the sum of the eigenvalues.
Okay.
It's half the sum of the eigenvalues.
Well, how do you get that?
Because the trace is the sum of the degrees, and we got handshake lemma.
Right, because the diagonal entries are the degrees. And so we say, aha, so using the trace of L, that's the sum over all vertices of the degree of our vertex, which is 2 times the number of edges, handshaking lemma. So L can tell us the number of edges. All right, good. Okay, well, that's lots of good things that we can get. So, all right, well, we should try to do some things about the spectrum. Well, first thing we should note is there are some things that we can say, we recover a lot of things if they're regular. We like regular things. So let's suppose for a second G is K regular. Okay, so we have lambda 1, lambda 2, up to lambda n are the eigenvalues of our adjacency matrix, because we spent a lot of time finding eigenvalues of our adjacency matrix. Then the question is, what can we say about the eigenvalues of the Laplacian matrix?
Oh. It's just the eigenvalues minus k. Minus k. Oh, it's negative of that, yeah. So it's k minus the eigenvalues.
So it's k minus lambda 1, k minus lambda 2, k minus lambda n. So can you sort of justify why that's true?
Because L is just k times I. So
because
T is k times I.
Because all the degrees are the same, so that they all have degree k. So it's k times I minus a. And it turns out that if you're an eigenvector for A, you also are an eigenvector for I. It's being an eigenvector for I is a very low threshold. Step 1, be a vector. That's not 0. Step 2, you're an eigenvector for I. And so that's why we can get that. Okay, well, that's nice. Well, let's see what we can do from that. Well, one thing that we can get, suppose we have the graph Kn. Okay, so the eigenvalues for A, does anybody remember what they were?
N minus 1, negative 1.
Right, n minus 1, and then negative 1. There were a total of n minus 1 times. Okay, so what are the eigenvalues of L? Well, so in our case, what is K? So what's the degree of the complete graph? n minus 1. So we take n minus 1, subtract n minus 1, gives us 0. N minus 1, subtract minus 1, gives us n. And so now we have the eigenvalues of the complete graph. Cool. All right. Well, we can, of course, do other regular graphs. Well, let's see some non-regular graphs. What if we wanted to do, I don't know, KMN? And I realize I need to go back and talk about why all the eigenvalues are non-zero. We'll get back to that at some point. Okay, KMN. Not so obvious. So, detour. All right. So let's suppose, let's say we have mu1, mu2, up to mu n are the eigenvalues of L for G. Now, I want to ask the question, what are the eigenvalues of L for G complement? Okay. Is it possible? So we should think about this. So if we have, for G, we have L is D minus A. Sorry, well, yeah, I should just put D minus A. What happens for G complement? Now you might remember we did something like this for the adjacency matrix, but we had to make an assumption. Do you remember what our assumption was? Regularly, this is where I'd give you a hint, but at this point I'd hope you don't need any hints.
It's regular.
What, sorry, what?
That G is regular.
Oh yeah, that's right. We need it to be regular. Good, okay. All right, see? You didn't need a hint at all. All right, good. Now, but of course, regular for us is secret code for what? For the adjacency. Being regular was secret code for saying what?
Is yeah.
The all ones. Ah. But what do we know about the all ones for the Laplacian matrix? It's always an eigenvector. You don't have to be regular. It's always there. Ah. And so, yet, maybe that's a reason to like the Laplacian matrix. Okay, so back to work. So how do we rewrite, or write, if you like, the Laplacian matrix for G complement? What do we do? What do we do? So here, I'll put a subscript L sub G. L, G, complement. And while you think about that, I'm just going to note, we'll make mu1 to be our 0 eigenvalue. Because 0 is always an eigenvalue with eigenvector all 1. Okay, I apologize. I interrupted your flow. So sort of think of it as sort of two pieces. How do you rewrite the degrees?
It's going to be like D minus n times I minus the adjacency matrix of the complement of G.
Well, we're on the right track. Okay, so let's think locally. So locally, I'm at a vertex. I look at the complement. What's happened to the degree? Yeah, it's n minus 1 minus the degree, right? So for just the degree part, we could do n minus 1 I minus d. So that's our new degree. Then for our adjacency, we talked about the complement of the adjacency. Do we remember how to do that?
Swap all the zeros.
We swap all the zeros and ones except
Those at the diagonal.
the diagonal. So how do we represent that?
J minus I.
J minus I minus A. Okay. Whew. Now, some nice things happen. We have some bunches of i's. We have n minus 1 i's, and then we have a plus I. So that makes an ni. We still have that minus the degree. That's fine. Then we have minus minus A. Well, that makes a plus A. We'll probably play with that in a second. And what's left? A minus J. Okay. So maybe we can write this as Ni minus J minus. And here, this looks a lot like that. And so it's LG. Okay. So, what happens? Well, one thing is, we always have our zero eigenvector. Well, sorry, I should be careful here, because that makes it sound like zero vector. No. We always have a eigenvector for 0, which is the all ones. And so that one is still going to stay as 0. Now pick a non-zero eigenvalue. Okay, I should be careful here. Pick a other eigenvalue, which has an eigenvector perpendicular to all ones. And we can assume that the remaining ones are perpendicular to all ones. Even if some of them are 0, that's still okay. We can still make that assumption. What happens to the rest? Well, so if we have, we'll just say x is perpendicular to the all ones. And we have d minus a x is mu x. So this is just saying I have an interesting eigenvector. I don't want to call the all ones eigenvector trivial, but it kind of feels that way since it's always there. So ni minus j minus Laplacian of g times x will give us
nx
Mhm.
minus 0.
right? nx, 0x, and the 0x comes from being perpendicular to all ones. And here,
Minus mu something x.
yeah, minus mu x. Because really this is our LG. So we get n minus mu x. So this becomes n minus mu 2 dot 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 n minus mu n. All right. So we now have enough to actually talk about KMN. So how will we do it? Well, what we'll do is we'll look at G complement. So what's the complement of KMN?
You have two complete graphs.
It's two complete graphs. It's Km union Kn. All right, so first off, let's talk about those eigenvalues. What do we have? We have 0, and then we have a bunch of m's. And how many m's do we have? M minus 1. What else do we have? Some n's. And we have n minus 1 of those. Anything else? Another 0. Yeah, because we'll get 2 zeros because we have 2 components. Okay, well now we want to take the complement of that. Right? So it turns out the complement of the complement, we get back to where we started. All right, so now we have to think about it. How many vertices are in this graph K, M, comma, N? M plus N. So where we had n up here, we have to put in n plus m. So the first eigenvalue 0 goes to what? 0. Because that's the one that's going to be attached to the all ones. The second eigenvalue 0 goes to
M times
hmm?
M times n.
Well, not m times n.
Oh,
It's
n plus n.
m plus n. All right, the m's go to what? They go to n's. And there's going to be m minus one of those. And the n's? Indeed. They go to m's. And there's n minus one of those. And so that's kind of nice. The spectrum of the complete bipartite graph. These are what we call nice numbers. If you remember for the adjacency matrix, we had a bunch of zeros, which are nice, but then you had this plus or minus a square root of mn. Like, not so nice, but good. In a same way, we could talk about joins in general. So as a reminder, we have joins where G plus H, and the idea is you take a copy of G, you take a copy of H, and you add all edges in between. That's the join of G plus H. But there's another way to write the join of G plus H, which is to say you take G complement, union H, complement, and then complement. And the great thing is, we know how to take complements, because that's this. We know how to take unions. It just says you copy them down. And then we know how to take complements again. And so it's easy to find the eigenvalues for joins. Should we actually do it, or do you just trust me?
Let's do it.
Let's do it? Okay, all right. How many vertices do you want G to have?
7.
Well, I was thinking like M or N. M. And H?
And 7.
And
I was scared for it.
okay. All right, so we have to sort of, just carefully work through our layers. And whenever I talk about layers, like I tell the calculus students, we call these onion problems because there are layers. You have to work through them. And we also say it's an onion problem because tears may be involved by the time we get to the end. So let's start by saying, suppose we know G has eigenvalues, and we'll just make a list here. 0, lambda 2, up to lambda m. So here's our eigenvalues for G. And our eigenvalues for H, again, we'll have 0. We'll do mu2 up to mu n. Okay, so first thing, what should we compute? As we go through and try to figure this out.
Eigenvalues of complements.
Right, we should figure out the complements, our innermost layer. Okay, so here we go for the complements. The eigenvalues for G complement. Okay, so remember, we have M. So what happens to the 0? It stays 0. What happens to everything else becomes M minus. So m minus lambda 2 all the way to m minus lambda m. Eigenvalues of H complement. Again, the first 0 stays 0. Everything else you subtract n minus. N minus mu2 up to n minus mu m. Okay, so we found the eigenvalues of the complement. Now what? What do you do? What do you do? Working our way. So we have G bar, we have H bar. We do the union. Now, oftentimes we don't say this explicitly, but we should at one point in time at least say it verbally, out loud. When you're trying to find the eigenvalues of the union, what do you do? Yeah, you do the union of the individual parts. And that's because you can always represent the matrix as a block matrix, where each block is the corresponding matrix for each part. Okay, so what do we get? Well, we get a 0 and a 0, and m minus lambda 2 out to m minus lambda m, and an n minus mu 2 out to n minus mu m. Oh, yep. Oh, wait, I said m. That should have been an n. Sorry about that. N minus mu n. Now what? We're almost there. This was easier than I thought. Complement. Okay, so the first 0 stays 0. So we have 0. The second 0 becomes m plus n, because we have m plus n vertices. Now the next batch, what will happen to those? We're going to take m plus n, subtract m minus the lambda, but does that simplify? Yeah, so the m's will cancel, and the minus becomes a plus. So you have n plus lambda 2 out to n plus lambda m. Last part, the n minus the mu's become what? M plus the mu's. And there we go. All right, good. So joins we can do. Easy, easy. Well, maybe not super easy, but easy-ish, easy-ish. All right. Okay. So I skipped a couple of things to say. So going back here, we know our Laplacian looks like d minus a, and we can just pick on an example. We'll give the PA graph a short respite. Say, okay, so I can't remember what the name for this one is. So yeah, it's this graph.
That's the word.
Well, you know, there's lots of ways to describe it. You know, it's a chorded C4, it's K4 minus an edge. But, you know, you're kind of like, oh, is there like a cutesy name? I'm sure there is. It's just the way graph theory is. There's lots of cute names out there. It's one of the downfalls of graph theory, actually, is people come up with these great names, but then the problem is you get like different people come up with different names for the same idea. And then you have to figure out, wait, are we talking about different things or are we talking about the same thing? And sometimes you're not really sure. It's one of the reasons why definitions in math are so important, because it's like, wait, are we agreeing with each other or not? I'm not really sure anymore. So, but okay. So if you fill in what you get, you'll get the following for the Laplacian. So we talked about quadratic forms, and that's one way to argue things are positive semi-definite, and that works. But there's another fun fact, which is Gersh-Gorwin's disk theorem. And I don't know, do people know this result? You know the name of it, okay. Just because it's so fun to say Gershgorman. And I will say I'm not 100% sure on the spelling of Gershgorman, but if you ask the internet, it's not 100% sure either. So it's okay if I'm off a little bit. Somewhere there's a spelling that will agree with this. Okay, so you know the name of it. Some people say, yes, I know what it is. What is Gershgorman's disk theorem? For someone who said, yes, I know this.
You can find all the eigenvalues in the union of disks centered at the diagonal entries of your matrix.
Yeah, so what you do, and now, so the cool thing about the Gershgorman's disk theorem is it works for any matrix. You don't have to assume it's nice entries, can be complex entries. You don't have to have symmetry. It can be messy. And so what it says is, says all the eigenvalues of a matrix M are contained in the following region. And the region is a collection of disk, and hence the name Gershgorman's disk theorem. So it is the union I equals 1 to n, so I'm thinking of M as an n by n matrix, of the set of points where you have z minus mii. So absolute values, just think of that as distance. And so I'm saying distance away from the center is your diagonal element is less than or equal to the sum j not equal to I of absolute value mji. Now this looks weird if you're not used to what it says. So the key here, we'll do it in terms of the Laplacian, is you look on the diagonals. The diagonals are your centers. So for us, in our specific example, so here's our complex plane, and we say, all right, so what we do is in the first row, we say the center is at 2, and now we add up the off-diagonal entries in that first row in absolute value. And what do we get? We get 2. So we're going to have center at 2, radius at 2. So we form a disk. That's a disk from the first row. From the second row, center is at the diagonal element, which is 3. And what's the radius? 3. Okay, then we keep doing this. Center is at 3, radius is 3, okay. And that last one, center is at 2, radius is 2. And now, if you take the union of those 4 disks, even though it looks like we've only drawn 2 disks, but there was overlap, it says all the eigenvalues have to be inside of here. You can actually do it, there's a stronger result about the multiplicity of the eigenvalues. And saying, well, this, if your disk are disjoint, then it turns out you can say, well, there's an eigenvalue in this union of disks, so many eigenvalues in this union of disk versus so many in that union of disk, and so forth and so on. It's really beautiful and surprisingly easy to prove, but not 10 minutes surprisingly easy. And so we will probably skip it, unless at some point in the semester we're like, we need like a half hour. Let's go back and prove Gershgorman's disk there. But okay, so what's the punchline? The punchline for us is that for our matrix, look at where our eigenvalues can be. They always have to be in the part where you have the real part greater than or equal to 0. And so we can't have any negative eigenvalues. And because we know our eigenvalues are real, because we're dealing with a symmetric matrix, it really says, hey, all our eigenvalues have to be there. All right. So that's another way to argue. That's sort of like pulling out a big hammer. Let's pull out a little hammer. And but this will be important for what's coming, a shadow of things to come for next week. And that is, I want to talk about something called the signed incidence matrix. Now, we've talked about the incidence matrix before. So let's just remind ourselves, what is the incidence matrix?
It shows where vertices are incident to edges. So so you have like rows represent vertices, columns represent edges, and then you put 1 if this vertex is incident to this edge, 0 otherwise.
All right, so you want vertices on the rows? Okay, cool. You can do that. You just make a choice. There's one of 2 options. And no, I'm not saying it's wrong.
No, I didn't read the signed.
Right. Well, we talked about the incidence. We got to get to the sign. And we'll see the sign. It'll open up our eyes when we see that sign. Okay, so we have vertices and we have edges. So in particular, not very square. So this is not a matrix which we can talk about eigenvalues. That's out. There are things we can talk about, and we'll get to mention a few of those later on in some applications. Singular values we can talk about. Okay, so, but again, I have a u, v, and I have an edge e. So E will have 2 non-zero entries. So I'm thinking here as E as the edge UV. Now, the incidence matrix is 1 if you're connected, 1 if of that vertex is in the edge. The signed incidence matrix says, well, for every edge, you pick a vertex and you say, you're the +1. And you pick the other vertex and you say, you're the -1. Now, at this point, you're probably going to say, which one gets the +1 and which one gets the -1? Aha! Doesn't matter. And the answer for us is no. So it's an arbitrary choice. Now you can try to make it fancy and say, well, I'll come up with a rule, but it won't help you. You won't get anything from such a rule. Okay, so we have to come up with a name. Unfortunately for us, I is out. So anyone have a favorite letter of the alphabet? J. J is also out.
T.
T. Sure. We won't have a matrix called T for a while. Okay, so we'll call T our matrix here. Okay. So now, question. What is TTT? And in case you're asking, that's T transposed.
Yes.
Sorry, what?
Most notably, it's square.
It is square. Yes. And in fact, if you think about the sizing, right? You have edges, vertices, and then it's going to be, vertices, edges, and vertices. How big will it be? Vertices. We'll see. All right. Now, when you're taking something like TT transpose, what is it you're really doing? Have you thought about that? What does it mean to take T transposed? Okay, well, I'll tell you what you can think about it. You can think about it as you're picking 2 rows of T. I'll just happen to pick two rows here, like such. And now, what you're really doing is you're doing the dot product of the rows. Because what you'll see is you'll get, say, the row here is your U, and then that column becomes V. So it's dot products of rows. So that should be our mindset. Okay, so TT transpose. What do we get? Well, there's a couple of cases. let's first off, what if U equals V? So we're taking the dot product of a row with itself. What do we get?
The number of edges of some.
That's right. It's the number of edges that are incident to it, because we'll get either 1 squared or a minus 1 squared every time there's an edge. And so, of course, it doesn't matter whether it's plus 1 or minus 1, we're squaring. So the number of edges it's in, that has another name.
Degree.
It's the degree. So the degree of the vertex. What if I pick 2 vertices which are adjacent? What will be the result? And I'll point out here that that is the case. Well, so if we pick 2 different vertices, it's for each edge that connects the 2 vertices, what will we get a contribution of? Minus 1. And so if we keep our graph simple, that's right. So if we keep simple, it's minus 1. And so that's because every other edge, you'll have things like it'll just miss that completely, or maybe it'll hit one, but not the other. What if we have distinct vertices which are not adjacent? It'll be 0. Okay, do we know any matrix which does this?
J minus the adjacency matrix. Is it not quite J?
This is the
N
Laplacian.
Yeah, it's L. This is the matrix we've been talking about today.
Oh, gee, maybe the one that's relevant.
Right. What are the odds that we'd actually talk about a relevant thing? Sometimes we goof and that happens. And so this comes back to saying, well, if we look at X transposed LX, this becomes X transposed T transposed X. Okay, well, not the nicest way, but we'll live with it. I'm going to think of this as 2 things. Is there any way I can make the first thing look a lot like the second thing? I can take the transposed of that. So this is T transposed X transposed times T transposed X. Is there another way for us to write that?
Dot product.
Right, it's dot product. But dot product of a vector with itself also is
Length squared.
the magnitude. T transposed X squared, which is greater than or equal to 0.